we are, dipping our toes into chaos. And we have gotten to the point that I know very intimately. Strogat's book is okay. So what I will try to do is I will try to explain to you why I think, and not only me, why I think what happened in 1976 was a big deal in 20th century physics. Not directly, but in some general sense, this year Nobel Prizes are meant to celebrate that. Now, what happened in 76 was discovery of universality in period doubling, or a renormalization theory of description of transitions to turbulence. So the original intent, and the intent that we still struggle with, of this work was to understand what happens when you keep turning up the heat under your pot of water or pot of oil on your burner, and at some point it goes turbulent. But as a physicist, you would like to know in detail, in some interesting detail, how this happens. How do you go from ordinary, regular behaviors that we have seen in 1 and 2 dimensions, part of this course, to a chaotic behavior, which we have seen in the model of weather designed by Lorentz? How do you get there? And there are various ideas. The most important idea, you have to understand that until 1970s, most physicists, except those making nuclear weapons, had no numerical computation and no significant ability to do difficult computations that can only be done numerically. So all the ideas until that time were kind of in cycles and epicycles. They were sort of, harmonic kind of ideas, going all the way back to Babylonians and Greeks, and because that's the only thing we could think of. So the way that people thought things got turbulent. Now, we have a very good visual image of turbulence because we know about fluids, we know about water, we know about air as humans. And Leonardo da Vinci was able to draw amazing sketches of turbulence and also of tornadoes and earthquakes. He has a book of drawings which is in possession of Elizabeth, Queen of what's currently England, which is just totally amazing because he draws things which are impossible to draw, which are turbulence, earthquakes, and storms. Examples of, in different ways, examples of chaos. So the prevalent idea until 1976, roughly, or beginning of 70s, was due to two people. One is Landau of Landau-Lifshitz theoretical minimum, something that none of you will learn, but very good Russian students and people who were within Soviet orbit used to study in great detail. These are amazing books. And what happened to Landau, at some point, he expressed a negative opinion about the dear leader, the self-elected president, not of Georgistan, not of our republic, but of Soviet Union. And usually things were advanced enough in Soviet Union that you would get killed for that. But first they would put you in jail in Lubyanka prison in Moscow. if you were in Moscow. Landau was left in an empty room in isolation, as he was a very important scientist. They didn't put him together with usual criminals as they do to political people. He was in a room without paper and a pen. He was not allowed to do anything. So he was only allowed, well, he was not allowed, but he practiced thinking. And he decided that the thing he should think about is how the turbulence starts. And the idea that he had was that you have first an oscillation of fluid. And we know that, there's so many experiments, and they're essentially harmonic oscillations because that's the only thing we could solve analytically or think of analytically was oscillatory motions. Then, and we know that too in great detail, if you push a system a little bit too hard, it's oscillatory, but system that has many degrees of freedom like a fluid, a new oscillation sets in. And then you get a behavior called quasi-periodic behavior. It's periodic, but it has two rotation rates in different directions in state space. And if you look at it in Fourier space, you observe two sharp frequencies. So it's a system. It's a little bit more complicated than a single oscillator, but not much. It's actually, two oscillators coupled. And then he said, well, if you push it a little bit more, there'll be more oscillations. And if you have enough of these oscillations, it'll look like turbulence to you. How would you know that this is quasi-periodic? Landau was rescued by Kapitsa, who was very highly respected low-temperature physicist in Soviet Union, who explained to Stalin personally that if he kills Landau, this will interfere with the nuclear weapons project in Soviet Union. So he was not killed. He was released, sent to Gorky, to a provincial capital. Another attempt at understanding turbulence was done by Eberhard Hopf. There were two Hopfs. They were German. There are lots of things in physics and mathematics called Hopf something or other, and they turned out to be either one Hopf or the other. Our Hopf is called Eberhard. As was custom in the 1930s for Germans who were not Jews, of Jewish origin, they became Nazis. So Eberhard became a Nazi, and he had to be rescued after war, along with Werner von Braun and other wonders of American science. He had to be rescued by a very prominent mathematician in New York, and he was brought to the United States, where he was allowed to do stuff in peace. So he thought about turbulence as well. Now, he had lots of paper and he was much better situated than Landau, but still he came up with, a more polished mathematical version that turbulence is lots of oscillatory motions, so many that they look complicated to you beyond your ken of understanding it. And so was our understanding of transition of turbulence until, let's say, late 60s, 70s, where a Dutch mathematician, Takens, and French, originally Belgian, mathematical physicist Ruel thought about this and said, look, there is something wrong with this, because if I have two oscillations and they couple, if coupling is strong enough, they will lock in. We actually worked out some of examples in this course already, when we had two people running around a stadium, and if they were locked enough, they eventually run at the same speed around the stadium. So they say, but it's there's lots of friction, there's lots of this. It's very hard to understand why these things wouldn't couple. And they proposed another transition, which is called Ruel-Takens transition to turbulence, which had to do with if you had more than two modes nonlinear coupled, they would become turbulent in a way which was not very clear, but experimentalists were trying to figure it out in late 70s or 80s. And then out of nowhere, and that's what's good about physicists, if they're good, they come out of nowhere, came a very different theory of transition to turbulence, which said that the turbulence happens through a series of bifurcations. Okay, everybody can believe this. But not only does it happen this way, but that there is a beautiful theory, renormalization theory of regime close to turbulence. And this was an incredibly powerful stimulus for physicists to give up on condensed matter and statistical physics kind of problems and follow this one, because in quantum field theory, statistical physics, and in chemistry and lots of other honorable subjects, there was a theory of phase transitions that said when you come close to, water freezing into ice, but that turns out to be a very difficult problem, but there are many easier examples of phase transitions. When you come very close to the border of transition, you actually forget what material you live in, what are you actually looking at, and you get so-called universal exponents. This has happened simultaneously and, stimulating each other in condensed matter physics and high energy physics. And Ken Wilson won a Nobel Prize for his theory of renormalization, which is kind of apex of this work, which occupied many, many physicists in 60s, 70s, 80s, and there is still a significant fraction of physics that looks for universalities. Universalities are nice because the usual materials are very messy. The world is very messy. And if you can find some characteristic of the world that doesn't depend on particular realization, you call it universal, meaning there is a whole class of different problems that all can be described by the same theory, and you can measure the same numbers in them, which are universal scaling numbers. You're very happy because, as you will see, it can happen in chicken hearts. Professor Fenton showed you rabbit hearts, but it was first measured in chicken hearts. It can happen in helium-2, 3 mixture at close to the absolute zero. It can happen in pipes. It can happen in amplifiers. So when your speaker goes in overdrive and starts getting noisy, it might be going through this universal periodic transition. So there was suddenly a vast number of experiments and theoretical settings in which you could be gainfully employed figuring out how to use this approach to renormalization. This was a big deal in physics for maybe a decade, but we are practical people. So after we have exhausted what could be mined in this problem, we have moved on to do other stuff. But it turned out to be so inspiring in mathematics that it's a very active branch of mathematics right now. I've given talks in leading mathematics centers on renormalization theory as late as 4 or 5 months ago about our work on period doubling. And it's so remarkably advanced that the formulas that I myself have invented, I do not understand anymore when mathematicians explain them. So the things have gotten very sophisticated. You have to be really, really good to do this, and it goes on. So it's a sort of interesting cultural thing, you know, cross-fertilization of fields. It wasn't necessary. You know, there are things like special relativity and general relativity which were necessary. You know, somebody had to invent them at that point in time, because by that time we knew we had Maxwell's equations and we had Newtonian gravity, and you had to put them together in one theory. So you knew what to do. You know, quantum mechanics was different. Nobody expected that. It was just a crazy new thing that happened that only young people could do. Period doubling has this quality, though, you know, doesn't have such important repercussions as the two fields, but it has a great cultural repercussions, because before that work, no physicist or chemist or engineer knew about chaos. They only knew about oscillations. You know, they're really indoctrinated in particular way of thinking. If, as experimentalists, you observe what we call chaos today, you would kind of not publish the data or put it to the side, because obviously there was a problem with your experiment. You know, it was Lorentz first who looked at his irreproducible data and realized, wow, this is deep stuff. So that's the big picture. And I wrote notes. I wrote, you know, a popular introduction to it on which Strogatz is largely based. So I'll go through my own popular introduction for a little while, and then we'll do a little algebra. And I think there is too much in this to do in one lecture. So even though Professor Fenton doesn't want me to teach anymore, I will do another lecture on this. So let me first walk you through my, you know, physics introduction to renormalization. And, you know, you have to understand what's happening now is nothing prepared anybody for this until it happened. You know, nobody needed period doubling universality. So basic idea of, you know, transitions to chaos is Yogi Berra's saying, when you come to a fork in the road, take it. If anybody in this class doesn't know who Yogi Berra is, you know what Google is. It's a worthwhile expedition. So I'll try to explain, you know, how it came in physics. What we knew by that time quite well experimentally, our colleagues, in particular, low temperature physicists called Lipschabet, knew how to take little containers of fluid. In this case, it was helium-2, helium-3 at supercritical, at very low temperatures in millikelvins. And when you do something like that, you go from a pot of water boiling on your stove to a low temperature lab where everything is controlled to, you know, many significant digits, thousands of percent. He was able to look very carefully what happens to a little box of fluid, you know, heated from below and cooled from above. So it's the same starting point as Lorentz's in flat planet Earth prediction, but this one is not on an infinite flat Earth, but in a very small container. And what people have observed, and all the fluid dynamicists have explained analytically and kind of with topological idea, is if the cell is sufficiently small, when you start heating it, the first thing that will happen is there'll be some place where the fluid starts going up And if you have wall, it's natural that happens in the middle of your cell. And by conservation of fluid, if hot fluid is going up in the middle, cool fluid from the top has to roll down. And that was indeed observed. So one observed rolls, rotational rolls, as the first way of transferring heat beyond just diffusion, which is very small. So once these so-called convective rolls started, they just go on, and if you keep temperature controlled very well, you can measure them forever. And then you ask yourself, and that is harder thing to guess, what happens is if I keep increasing temperature in very small increments, at some point something has to happen, because I know if I do it in a huge increment, I'll get turbulence, right? So something should happen. And indeed, what's observed is that if you look at the roll, it rolls, it has this rotational motion, but it starts changing its shape, so it starts oscillating. So waves, oscillatory, small disturbances develop on the roll, that this thing in time is, writhing a little bit. And the way you measure this, it's very hard to see a small cell of helium in a door at very low temperatures. So you put the thermometer, they call it bolometer in the trade, at the top someplace, at 1/4 here, and you measure the temperature. And that sort of is a way to see what's going on. And you get the time series. And temperature, it looks like that. As time goes, as the roll goes back and forth, you get more hot or more cool side of the roll. And you observe an oscillation. And in the beginning, this is a, nice sinusoidal oscillation for close to the transition. And pretty soon you realize, this is a stupid way to look at your data. I mean, people tend to do this first, to look at the state of your system as function of time. Time goes off to infinity, so you need an infinite strip of this information. However, if you, instead of using time as another variable, you use, for example, speed of the change of temperature. So, your bolometer tells you where the ridge is, but if you take derivative of that measurement, that's a speed derivative in time. And if you plot them against each other, the deviation, distance and roll in this direction is bounded. And the thing doesn't speed up crazy, it goes this way and it goes back, so it suddenly has to reverse. And you obtain a plot where you have a circular motion. And you are familiar with this from our plots of harmonic oscillator, where we plot position of the end of the spring and its momentum. But it turns out you don't need classical mechanics. You just need position and change of position, rate of change of position in, no matter what you're measuring. So first thing that people learn by doing the experiments, that the intelligent thing is to look at them in state space. This is fluid, so state space should be infinite dimensional. But it turns out, no matter where you stick your thermometer, you get something like this. So it might be infinite dimensional, but effectively just one dimensional. It's just motion on a circle. And no matter how you look at a circle in this high dimensional space, which measurement you take, you just see, a circular motion in all cases. So topology will be the same. So that's pretty straightforward. And then people know, and in the 1970s, that was a logical necessity of life. Experimentalists had boxes, maybe they have them still. They're called spectrum analyzers. They're very expensive. Hewlett-Packard was making them. If you had one of the boxes, no matter what data you got, you would feed it into that box, and you would measure the frequency spectrum. And not surprisingly, in this experiment, people notice that there is only one frequency. It's very sharp. So how wide this little peak here is depends only on how well your spectrum analyzer matches it. So that was the first thing. But now what Lifshabir did is he kept on looking and increasing the heat from the bottom. At some point, he discovered, by looking very carefully, that the period was no longer what he thought the period was. It's called tau zero in this picture. But it was actually twice tau zero. Now, it's very hard to see this in time series when it happens. But if you plot it in this phase plot, you realize that you go around, but you don't rejoin your initial point. You send for another tour around, and then you rejoin. And if you measure its Fourier spectrum, what frequency components are important, something unusual happened. You know, what usually happens with a perfect oscillator. When you measure Fourier spectrum, you get one frequency. But if the motion is not perfect, so it's not really running on a circle, but it has some deviations from the circle as it goes in phase space, you need more Fourier components. And the usual situation is that there is a fundamental frequency of your instrument, and then there are various harmonics which are either a problem because they're distorting quality of the sound, or they're desirable because they give you kind of sound you like. But this was totally different. You got the subharmonic, you know, that people were not used to. You got a frequency which was half of the original frequency, and period was twice. Then Lifshabir increased temperature a little bit more, very carefully. And at some point, even this thing was not coming back to itself. So you would go around once, you miss. You go around twice, you miss again. You go around 3 times, you miss again. And only after 4 times, you would actually come back. Now, that's getting pretty weird. When you look at the spectrum, you have a dominant basic frequency. So the basic motion is that period with some deviations. So frequency is very sharp. So this subfrequency turned out to be weaker. And then there was a fine scale in this problem that corresponded to 2 more frequency peaks. So you discover something where your period doubled and then doubled again. And experiments usually stop here. It's very hard to push them beyond that limit. But if you have equations that you can put on a computer, you can go much further. So in practice, all the experiments that observe period doubling, of which there are very many, it's totally standard thing today. So you just say, I saw period doubling and then I did something. In practice, if they observe period of length 8, they're doing very well. And sometimes period of length 16 can be measured, and that's about it. That's heroic undertaking. So this is the experimental situation. Now the theory was actually done a couple years earlier than the experiment, but experimentalists didn't know about the theory because nobody knew about the theory except a very select group of theoretical physicists who got excited. So, it takes a while to percolate. So these things happen simultaneously for all practical purposes, but experimental observations had no theoretical justification. What one then does as a theories. One does kind of things that are now described now textbook material in Strogat's textbook. You say, well, it was like an oscillator, so that meant the acceleration was proportional to the displacement. This is first and third term. But it's a fluid, so it has friction. So there was a friction coefficient times velocity, we know that. And really, this is not a harmonic oscillator, this is some complicated thing. So it's nonlinear, and simplest nonlinear, it's called quartic oscillator, but simplest nonlinearity is 2 powers up from x. Ignore this 4, that's for convenience. To make this experiment run, you have to force it. And you can do it by constant current, or you can force it by some crank outside, which is periodic crank. So you've seen this before. It's this kind of oscillator, and you've learned about bifurcations of this kind of oscillator. But now you're going to do, and we won't do it because we'll discover that maps are much more intelligent way to think about it. But in numerical experiment, you would change something. For example, you would drive system harder and harder. This amplitude would increase. That's one possible way to getting a system to behave chaotically and turbulently if you really push it. And you do experiment, and same thing happens. You discover that for sufficiently small driving, you either have a limit cycle or a cycle that's twice its length. But then as you very carefully move this thing around, you go to increase it gently. You go to period 2, 4, 8, etc. You can change the driving, or you can change the friction. So if you decrease the friction, if friction is very strong, you're sent to a limit cycle, because for strong friction, you're just following the orders that come from here. But as you decrease the friction, instabilities will set in. Decided to draw everything by hand, but this was, a hand rendition. What happens in this system? One observes limit cycle, 2 cycle, 4 cycle. So this is what you see both experiments, and you see it in numerical experimentation. And there you can do, more careful and more perfect realization of the system. And one keeps seeing more and more sub-frequencies. So there is first, a single Fourier mode, then there are 2, then there are 4, then there are 8, and they get weaker and weaker. And this goes on. And the natural question a physicist would ask, well, does it stop? What happens? Does it go on forever? And that's what we'll discuss. How does it do it in detail? So now let me say what was the big deal. These experiments, the systems have some knobs you can control. They might be called Rayleigh number or Reynolds number or whatever your physical system is, or they could be called, cellular voltage, as in Fenton's example. The other thing that's very important is these systems are dissipative, they have friction. So what happens if you start them in some weird way, they might have some complicated transient behavior, but then the transients die out and you're either on a fixed point or some periodic orbit or something like that. The other thing that turns out to be quite important, more important than appreciated, is that the container, the boundary conditions for your fluid have to be, it's called small aspect ratio, but that basically means is that dimension of the box are roughly the same size. So maybe height is 1, width is 2, length is 3, but they're all order 1. If you have to look at very long or infinite containers, that's called a channel flow, things might look quite different. If you have to look at them very wide, that's called coed flow. More complications come in. So for this theory to really work for you nicely, you need situations where your phase space is quite constrained by the geometry of the problem you're looking at. So now comes the surprising set of results due to Mitchell-Feigenbaum. He discovered and then explained that there are some ratios in these observations that go to universal limit no matter how you get started. Now, you have to understand this is happening, what's called curiosity-driven research. Nobody asked Feigenbaum to solve the problem of turbulence. You know, most physicists were supposed to solve the problem of quark confinement at that time. They were, but he found, you know, he had a PhD in that kind of thing, but he found it rather uninteresting. So he pursued whatever he found curiously interesting. And he observed first that the way you have to increase the heat in your system, you have to do it in smaller and smaller steps called delta. And the ratio of this step, ratio of how you have to change the parameter, was going to a universal number, a number which we now know to 1,000 digits or more probably, which is not, as far as we know, related to any of other numbers we know. You know, it's not a pi or a combination of pi. It's not, you know, whatever Catalan's number, whatever numbers we happen to like. It's none of those. There are some important numbers of mathematics, and this is a new one. But then he also noticed that when you look at the splitting between neighbors passing when they go through period doubling, that this ratio, the splittings, the distance of, you know, how long, by how much I miss in 8 cycles when I go halfway around compared to when I do this for 16 cycles, that also went to universal limit. So that meant the first one means you must have a very good control of your stove that's heating the cell. And most people didn't have it except low temperature physicists working at millikelvin because they were set up to such sensitive measurements. That's why it was not done in water first. The next thing is, you know, to notice that you're not periodic anymore, but you have to go twice around. You had to have a magnifying lens to resolve the neighborhood to see this. And that's meaning of the second number. Being a curious person, Feigenbaum tried to study different systems which exhibit period doubling. And he discovered first numerically and then explained it theoretically, or we explained it theoretically, that this number didn't care about what system you started with. So I'll show you some table of, you know, early experiments. I haven't kept track of them since. And that, you know, physicists love because that's a very lazy thing. You know, I don't care whether you're raising chickens, you must get 4.6692. So that's a powerful statement to make about, you know, rather limited sets set of situations because you have to look at transition to chaos or turbulence. And the other one comes for the right. So it says there is some scale in parameter and some scale in state space. This gives you predictions. So first way he used it was to estimate when I'll lose 8 cycles and get 16 cycles. This would give me very good starting guesses for period parameter values. This heights, this is resolution in state space. When you take a Fourier transform, you're measuring that resolution. So that tells you something about the strength of subharmonics. So there were 2 predictions, and they were verified in Lipsche-Beer's experiment. So people started paying attention. Now we see it every place. So I will give you an example here. So this is kind of graph. If you look at Strogatz has lots of these pictures. And there is a parameter. Now, this particular parameter, this particular experiment describes a flame front on a Bunsen burner. So you're in the kitchen, you have a circular gas burner, German one or Japanese, infinitely precise, very controlled Bunsen burner. And your parameter is the speed at which the gas exits from the edge of the burner. And you look at the height of the flame or velocity of the any point of the flame. And, that turns out to be described equations that are very similar to Navier-Stokes equation that describe fluids. So many people care about such systems. There are experiments, there are measurements, there is theory. In this particular plot, it's shown that it's a burner, it has a flame front, etc. That flame front is stable until certain value of so-called hyperviscosity or something. And then there's bifurcation in 2, bifurcation in 4. And now you can see the experimentalist problem. When you go to 8, it's only hard to see on piece of paper. And these periods are getting shorter and shorter because every time you increase the parameter by 1/5 of the previous increment, 1/5, you observe one of these things, but it's 1/5, 1/25, etc. That goes very fast. So resolving this is very hard. That's why experiments only see finite number of bifurcations. And same thing happens in a space direction. How far the branches of this period doubling, they get to be very, very narrow to each other. So experiments stop. It turns out that in this example, there are some other areas of regular behavior. There are these white areas here where you end up in a stable cycle of length 5, 7, and 3, the one that Michael Toye and Flavio are very proud of, that they could resolve that one. So this stuff is now everywhere, and we don't report on it as a discovery. When we discover a new system, we just observe the system exhibits period doubling. Now, what's nice about universality, once you believe it or can establish it, it's a more detailed blow-ups of, in this case, 8 cycle. What's nice about universality that, it's very hard to have a very expensive laboratory at l'École Normale Supérieure, subsidized by French taxpayers, to do low temperature physics. So, in Georgetown, in the basement of Howie, where we do this very expensive experiments ourselves. But what if you could do it if you just went fishing? Yeah, it's universal. So at the time when Feigenbaum discovered this, and we discussed it and thought about it. The only example that we knew at that time was what happens to population of a fish in a lake. What is this about? It's population theory. And it says, suppose I have a lake with some amount of nutrients that every year come to the lake because it's part of the natural cycle. And I have some number of fish in it. And then stuff that we discussed already happens. You write, as a population biologist, you write some equations to model this. And you find out that if there are very few fish in the lake, their number will grow from year to year until there's so many that they overgraze the lake and the population starts decaying. And you say, well, obviously it's nature, it'll stabilize at some equilibrium. So there'll be the same number of fish in the lake. The number of fish in a lake a year later can be written as one-dimensional maps. Very soon, realize it cannot be a linear map, so we try a quadratic map, or it could be some sines, cosines, Hermite polynomials, whatever, Chebyshev, whatever makes you happy as some base. And you get some approximation to number of the fish of the lake. And that's the only example we knew of this period doubling where we could show universality. And you've already learned it's easier to work with maps than with the flows. A map is just a Poincaré section of the flow. You can see that that's a sensible thing. When you look at this detail, if you know what's happening on the section, this line here, right there, basically everything about of the whole flow, because you can reconstruct the rest from Poincaré section, this. So we knew this, but the reason why we really wanted to do this was universality. What universality says is you have thin fish, fat fish, different kind of fish, or maybe not at all fish, but it's helium-3, or it's chicken hearts, or it's rabbit hearts, or it's whatever. Many examples. And all of them have robustness in the following way, that their transition to chaos, this period doubling, is characterized by same universal numbers. And the reason why we started to think about it and thought about it, and real motivation for everything, and I tried to describe it in a lecture a year ago, a popular lecture. The real motivation was that we said, look, brain is like this, all neurons are imperfect, they're all noisy, they're little biological things. Each one is different. They're good within specs, but they're, not German quality at all. I mean, they are 5, 10, 20% different from neuron to neuron. So what if brain is stable and robust because it relies on universalities? So this is the real reason why we do this. And you have to understand that's what physicists do. If we were engineers, they would have nothing to do with building a good bridge, and we would not be allowed to think about it. But as physicists, you're allowed to think. It's okay for you to think about how brain functions, even though your day job is, working as a Murigal slave, doing crystallography of some weird material. That idea turned out to be totally wrong, but it doesn't matter because the discovery turned out to be beautiful and, with great impact nevertheless. So we try to first understand, why is there period doubling? Why do you see this stuff? To do this, and we wrote the simplest possible, a map which is not linear. This was done first by mathematician Fatou in 1910 or so, so it's called Fatou map. So it's a quadratic map, and it's same as logistic map with small change of coordinates, which has one parameter and you change, and it has one nonlinear term, x squared. We had pocket calculators, Mitchell had extremely expensive one because Los Alamos Lab bought it for him. I had an extremely cheap one because my girlfriend who worked on the assembly line in Hewlett Packard could get it at 1/4 price if it was damaged. So I had a pocket calculator in which multiply and divide by interchange. But that was easy to learn. But anyway, so we could do this. And what do you do in pocket calculator? You program it and you put some number in, number comes out. And you press the button for the same program. So it's input of the next thing. And you do this over and over again. That's called iteration. What we discovered, I mean, we did the stuff that if I have time, maybe I'll do it next time, but I'll do the usual time. I'm supposed to compute fixed points and I'm supposed to do the usual stuff. The stability, but that's all straightforward and you know how to do it. If you read it in Strogatz, it'll be good. We understood pretty soon that there are some values of parameters in which iteration settles on 2 cycles, other cycles. And then we understood that as you did this many times, you had, at every time you did this, you had to look closer and closer with a magnifying glass to your cycle that was going to double. And you had to double it, meaning we had to apply the going around twice. We scale it, and we discovered that that actually goes to limit this process of blowing up and doubling whatever you have in period, which explain the period doubling. You know, why do you see it and why it's universal. So I'm supposed to explain it a little bit better. So there are 2 ways to see it. You know, one is to look at return maps of the kind we have seen in Rosler and Lorentz attractor. That's the picture on the top. The other one that I find very pretty is to do this in complex plane, but I'm not allowed to do this in this class. But it's if you do this stuff in complex plane, you have a very nice visual image of how things are period double and how they're self-similar, because the essential idea will be that small parts of parameter spaces self-similar to the larger ones. I'll give you now a sketch of how it works and how we understand it. And here is the main idea. When you have any fixed point of a map, now, if you, well, okay, let's just understand a single fixed point. Then a fixed point of a map is stable if the slope of the fixed point of the map at a fixed point is smaller than 1 in magnitude, because that means that a neighborhood at every iteration gets smaller and smaller. You shrink it to a fixed point. So you get some behavior where you start someplace and you just go into the fixed point. Then, as you make map nonlinear, you kind of stretch it out and its slope increases. There's a critical slope when the map itself has slope 1. And what happens at that point, your fixed point goes unstable and it has to do something. Now, you actually already know what it does. It's a pitch for bifurcation that you know. The fixed point goes unstable, but it gives birth to a period 2 cycle. Now, how do you understand that? If you look at the iterate of the function, it's the second function of the function, what happens 2 steps later in time? The way this works is that the iterate itself develops, a little kink and keeps the original fixed point, but now it's unstable, and produces 2 extra fixed points. You are now where you started, because now you have function, It has some number of fixed points. So now you say, let me look at this little window around here and what happens to it. That window is the same qualitatively as that picture. So when you look at the second iterate, it'll be first attractive, then the slope will increase. And then in this window, it'll period double. And that's why, the sequences of period doublings happen, because you keep losing stability of the cycle you had. And the only way it can, gently and naturally go unstable is through pitch bifurcation, where it gives birth to more periodic point. Now I can say this, but if you plot this is pretty crazy. So let me see what the function starts looking like as you keep iterating it. So what happens is that the function develops twice as many wiggles at every of this period doubling, your original function. And when you look at it on the original neighborhood, it gets kinkier and kinkier and kinkier. But if you keep blowing it up, it looks very nice and smooth, and that's what we did. Basically, we turned this into a machine which says, keep increasing your parameter, so make it more nonlinear, more strongly stretching. And what it does is always to one of these fixed points, it makes it unstable. And the only way it can go unstable is that when you look at its second iterate, you develop two new periodic points, and the old one goes unstable. So you always have to go in this neighborhood through two cycles. That's a necessary local property of what kind of bifurcation you can get in maps of this type. Then you magnify this neighborhood. And forget that this is part of a huge function, so you magnify the neighborhood. You observe that looks very much like that thing. And you keep repeating that. So you keep increasing your parameter to get instability, then magnifying the neighborhood of second iterate of the function. And this ends up in a limit that has a property that when I iterate this, I get the same function back. So that's called the universal function. And it's a function that has a property that you take original x, but you rescale the neighborhood by using this number alpha. So you sit in a smaller neighborhood for same value of x, and you iterate it 2 times. That's what these pictures are. These are second iterate. And then you go back to original scaling, original variables. So that's called conjugacy by this number alpha. You get the same function g back. So then I thought, wow, that's incredibly simple. Let me find out, what does Euler call this thing? I was working at Institute for Advanced Study, which has a beautiful mathematics library. It's physically beautiful. You sit on, chairs where Einstein used to sit, etc. And for weeks, I would go through books because I didn't know what this thing was called. So I would try this, and I would try that, and I would try that. And now, that was in 1976. There is still no book other than new books that has this equation. So this is the weird thing. It's such a simple thing. Euler didn't think about it. And it's not an Euler number. Feigenbaum thought about it. So the moral lesson is that you can do amazing thing tomorrow or 10 years hence, because there are infinitely many amazing things undiscovered ahead of us. It's not been all done in 18th, 19th century. What you learn in the books is just helpful, gives you some tools, but this is not the end of the story. This is the beginning of the story. Why did this thing become universal? Because the only feature you're using of your function that it's differentiable and nonlinear. And nonlinear means that it has at least x squared in it. It's a first nonlinear number. Only thing that's been used in formulating this function is that when you come closer to the border of periodic orbit of length 2 to the infinity, and this is where transition to chaos happens, that happens for the finite value of parameter. It happens in a way that's nothing like what Landau and Hopf told us to do. There was no way they could think of this, or maybe they could have thought of it, but they didn't. So it's totally, totally different. And because you're magnifying a neighborhood that's only controlled by being quadratic, and you're pushing away the details of the function away from your neighborhood, because every time you magnify the neighborhood, you increase the scale of the whole system by a number, which is roughly 2.5. All the stuff that belong to particular chicken or particular box of helium is going away, and you're only looking at the detail that controls how you approach infinite period cycle. So that was the big discovery. There is a next level to this, which you're kind of ready to understand, but not quite yet. Several surprising lessons. We started with fluid, and we reduced it in the magic of Lorentz to a one-dimensional return map. Totally remarkable. But now we have to describe this function g, which has not only quadratic power. We started with parabola, the simplest possible map, nonlinear map we could think of. But as we iterate the map, and again, I'll do it next time by hand. As we iterate the map, we start developing a function with infinitely many terms if you arrive at the Taylor expansion. So we're in a function space. So suddenly we're in an infinite space. And in that infinite space, there is an unstable manifold, it turns out, which is, there's one direction in which we can mess up these functions, which corresponds to our period doubling sequence. Otherwise, as we move in the space, there are stable manifolds which are codimension 1, because there's one unstable one. And this renormalization process is some kind of abstract process, but it just works like time used to work in our iteration of the maps. So you learn that there is not only time, but there are many other parameters in the world that describe different, very, very different ideas, which have the same quality that, you have to step one step, maybe not in a time, but step in this function space. So there are flows, they're called renormalization flows, which are not in time, but they can be described by the same technology of dynamical systems for evolution in time. People measure this, so let me show you some results. So at some point I compiled a table of experiments, which is amusing because there's so many different experiments. Where is it? Okay, never mind, it's in the notes. The amazing thing is you get these numbers. I'm not kidding you, chicken hearts. But more accurately, you get them in all kinds of chemical processes, electronics, you can make analog circuits, you can make bad amplifiers that go through period doubling, you can make fluids, superfluids, condensed matter things. Every place this happens. And this is now a totally different thing, unlike anything that's happened in this course before. This is a totally new kind of physics describing how you go from regular behaviors to chaotic behaviors.
Yeah, doctor.
Yeah, I do have a PhD, if that's what you... Yes.
Oh, no, I have a question.
Okay.
Oh.
I don't have it on my wall like real doctors, but yeah.
That when you come to a fork in the road, take it. So which way you go?
That's wonderful thing about your life and forks in the road. It turns out either way is good. But in your situation, you take one fork or the other, they're both good. So, which one you actually take often depends on very small microscopic conditions, like, who was your father? What happens after that is deterministic, once you have taken the one branch in this case. Now, in period doubling, it's kind of cute because...
So you have to take the fork anyway. You cannot not take the fork.
Well, you can decide to die before taking the fork, but... No, I'm not being serious. When you make systems, your intuition is this. When you stress systems more, make them more nonlinear. I tried to explain this in Bernoulli map example. As you have more and more stretching, that's called more and more nonlinearity. You expect systems to be more and more unstable, And it turns out even that's truth with qualifications. There are many subtleties. But basically, if you go beyond, simple oscillatory motions, and you go to the extreme where perturbations all grow exponentially rather than oscillate, which is a very natural thing when you look at local stability, then the intuition is more stress, more instability. You have no choice in taking the forks because you get more and more stressed. I mean, the system gets more stressed. In our case, the climate gets more stressed by us driving it in the way we are driving it. Things can be amazingly sensitive to small things. So small changes in parameter can have very large consequences. Popular thing is the butterfly effect, that you perturb something here and there is a major weather thing happening elsewhere. In detail, this is always not true, but in spirit, it's right. I mean, in spirit, it is right that deterministic system cannot be controlled beyond its exponential time of stability. So exponentially short time. For me, the purpose of this lecture, which no doubt failed, but the purpose of this lecture is to give you a feeling that we have gone from looking at little oscillators going this and there. The tools you need are totally different to understand chaos, because the thing is quite different qualitatively and in tools you use and the way you think about than anything we encountered in classical mechanics up till now.